that system, in homeostasis, the cardiovascular system plays a key role. Because it is the system that connects all of our cells, eventually, to the outside world. Any cells deep in the depths of our body can only exchange with the blood, and the blood then exchanges with the outside world. Okay? You understand that? Everybody understands it? Good. Now, what is the cardiovascular system? Oh, shit. Okay. Well, the cardiovascular system is a very complex system of tubes. A closed system where blood fluid is being pumped around by a pump, the heart. But actually, the heart consists of two pumps. So there are two pumps on the system. The left heart gets the blood from the lungs, loaded with fresh oxygen, and pumps it to all the tissues. In the tissues, the oxygen is given away, and CO2 and garbage is taken up, and that goes back to the right heart, which then pumps it into the lungs where it can be cleared. So a very complex system with two pumps in series. So the first basic rule of the circulation is, if you have those two pumps, they have to pump at the same time and pump the same amount of fluid. Otherwise we get into problems. If one pumps more, this will blow up. If this one pumps more, the lungs will blow up. Okay? So it has to be coordinated and synchron. Now, to achieve the exchanges, the tubes will divide, the blood vessels will divide into smaller and smaller parts. We have the large blood vessels, the aorta. We have the arteries. We have the very small arteries, the arterioles. We have the smallest blood vessels, the capillaries. And then they reunite to form venules, which forms veins, which form the large veins, which go back to the heart. Okay? And today we will try to discuss the function of all of that. Why did I do that? Okay. Now, the situation is a little bit more complex in that we don't have one capillary network, but of course the heart, the aorta will get out of the heart, the large artery, and then branch in a number of parallel circuits. So it's not one, if I go back one slide here, it's not one exchange system. But there are, several, each tissue, the brain, skeletal muscle, endocrine glands, stomach and spleen, intestine, endocrine glands again, the kidney, they all have their network, their capillary network. In the rule, there is only one network per tissue, but there are exceptions where it is more complicated and you have two in series, for example in the kidneys or in the liver. But we will leave that for today. So, to summarize, the assembly of the cardiovascular system, two balanced pumps in series, most circuits in parallel. There are exceptions where there are two capillary networks in series. Now what about the function? Well, the pump, Professor Peter Kang has told you about or will tell you about it, so I will not go any further in that. The oxygenator, the lungs, is covered in other courses. So today I would like to focus on the blood vessels, because that's what I spent the last 50 years of my life, is understanding how the blood vessels function. And I'm telling you, after 50 years, I still don't have all the answers. That's what makes research so exciting. That you start at your age, and then you go on, and at the end you've learned a great deal, but you still have so much more to learn. That makes research extraordinarily exciting. And it's the only job I know of that where you can have that up to, I'm 72 years of age, and I'm still as enthusiastic about research as when was your age. And I don't know any other job that can do that.
Still you're young.
Oh, well, not when I wake up in the morning. Okay, good. So the tubes, the blood vessels. Well, this is a cut through one type, the arterioles. Those are the smallest arteries before the capillaries. But it is quite representative. In all blood vessels, we find an internal layer, a tapestry, like this here, that covers the blood vessel. That's one layer of cells, the endothelium, a monolayer. Around that we have an elastic membrane, connective tissue. Then we have smooth muscle. Those are muscle cells, we will see. They contain contractile protein. They're arranged usually in a circular fashion around the blood vessel, so that when they contract, the blood vessel becomes, the diameter decreases, okay? Then we have other elastic membranes, and then connective tissue, which we call the adventitia, in which we have fibroblasts, nerve endings, fat cells, all kinds of cells are there. Inflammatory cells, possibly. So we always have to keep that in mind. So if we now cut through it, you see here the endothelium, the elastic membrane, the smooth muscle, the elastic membrane, the adventitia. And this is what you find more or less in all blood vessels. Again here, endothelium, elastic membrane, connective tissue, smooth muscle, etc. But not in all blood vessels to the same extent. In some blood vessels, this is very thick. In other blood vessels, the capillaries, we only have that. It can vary. And that is function to understand how the circulation works. All you need to do is know a little bit about hydrodynamics. You have to think about your apartment building and the water supply in your bathroom. Same rules. If we look at an apartment building, there is a water reservoir on top, okay? And that connects to the different apartments. And when you open the faucet in your bathroom, if you live close to the reservoir, it will flow, but not very strongly. But if you live at the bottom of the building, the flow will be much bigger for the same degree of opening of your faucet. Why is that? Well, because you vary the pressure. The basic rule that governs hemodynamics is the same that governs hydrodynamics. That is that in a tubular system, the flow, the amount of fluid that flows is function of two things, of the pressure and the resistance. If we go back to this, if we go back to this, the pressure and the degree of opening. The degree of opening is the resistance. And if you, for a given pressure, if the degree of opening is great, there will be a lot of flow. If the faucet is almost closed, it will only trickle. Okay? Now in our body, it never closes totally, because if blood vessels close totally, that's not good. So there is always a certain degree of opening. But that will determine that. And if we now look at the system, the pump generates the pressure, which then will go to the different tissues, and depending on the degree of opening of the resistance in all the vascular, in the individual vascular bed, more or less blood flow will go to any given tissue. Do you understand that? It's very simple. It's like your bathroom. The only difference is that in your bathroom, the water goes to the sink. Here, we cannot afford to lose it, so we pick it up in the veins and we recirculate it through the second pump that picks it up and sends it back. Okay? Very simple. So, remember, this is the basic law. It's like Ohm's law in electricity. It's the same thing. Pressure equals flow times resistance. If the pressure augments and the resistance doesn't change, the flow will go up. If the pressure remains the same and the resistance goes down, flow will go up. Very simple. So, and the definitions here, pressure is the pressure in the blood vessels. We'll come back to that in a second. Flow is the amount of blood. When we look at the heart, we talk about cardiac output. And cardiac output is the amount of blood pumped times the frequency. You've heard that. Stroke volumes times frequency. And then in the arteries, we talk about flow. Okay. I'm sure you've seen things like that too. If you heard about the heart is a pump, but it's a pulsatile pump, so it contracts and relaxes. And the pressure in the heart goes from near zero to about 120 millimeters of mercury and then falls back again. The blood is pumped in the blood vessels, and we will see that there we have a pulsatile flow too, but it doesn't fall back to zero. We will talk about that in a moment. But we make the distinction between systolic blood pressure, when there is full opening between the contracting ventricle and the blood vessel, then the pressure is nearly the same. It's a little bit less, but you cannot see it here. And then the pressure remains high during diastole, during the relaxation of the heart. And as we go down the blood vessels, the pressure drops. Why does it drop? Because the heart generates a given amount of energy, and every resistance that we overcome, we lose some of that energy. So that at the end of the loop, there's hardly anything left. And that's why we need a second pump to jerk it back up, to get it through the lungs. But in the second part of the system, the pressure is much less, about 1/5, 1/6. And you may have heard that in other classes. So, what do we have to remember about pressure? It's phasic, systolic high and diastolic low. It drops, oh, I didn't say that. The pressure drops, but drops mainly in the small arterioles and the small arteries. We will see that we call those the resistance vessels, because they offer the biggest resistance. And the pressure is 6 times lower in the pulmonary circulation. What are now the function of the individual blood vessels? Well, the first one that we need to talk about are the very large arteries. And they contain relatively little muscle, but a lot of elastic tissue. So they're elastic. And they fulfill what we call the Windkessel function. Now, you probably don't know what a Windkessel is. Let me go back a few slides. You see, if nothing happens, the water here will drop progressively, will it not? There is no pressure. So in an apartment building, what do we have? We have a pump system that brings the water and pumps it back in. So, for a pump to function, it can usually, most pumps are pulsatile. Now, let's take maybe another example, if you drill a well and you want to use water of that well for your home, some of you may live in the countryside or have grandparents who live in the countryside, they have seen that. Now that pump will pump water, but not directly into the system. It will go in a big reservoir, okay? And what is typical of that big reservoir, do you know? Is it full or not full of water? There is some air in between. Why do we want air in between? To act as a depulsator, so that the pump from the well pumps, and out of the reservoir we have a more steady flow. This is exactly what the arteries, the large arteries do. So as we have seen, the flow is pulsatile, and here, in the large arteries, it is not. And this is because they contain a lot of connective tissue, and when the heart pumps, they dilate. And when the valves of the heart close, so suddenly there is no pressure anymore, they recoil. And that will maintain diastolic pressure throughout the system. And this is particularly important for the coronary circulation. Because the coronary circulation, you know what it is, those are the blood vessels that go to the heart. Because when the heart contracts, the tension in the wall of the heart is so high that no blood can flow to the heart muscle itself. And it's only when the heart relaxes that blood can flow into the heart. And thus it is absolutely crucial to have this, for the heart, but for all blood vessels, to have this Windkessel effect. Here. So, the large arteries are the depulsator of the rhythmic blood flow that leaves the heart, and this ensures adequate perfusion and ensures continuous perfusion during the heart cycle. Remember that this is particularly important for the coronary circulation. Okay, the second type of blood vessels that we classically discuss are the resistance vessels. Those are the smaller arteries and the arterioles that offer the most resistance. Why are they the most resistant? Let me first show that. If we go back again to aorta, large arteries, arterioles, precapillary arterioles, and we look at the resistance, we see that the resistance becomes larger and larger as we get closer to the capillaries. And then in the capillaries, it drops again. Okay? And this is inversely related to the size of the blood vessel. The size is smallest here, and then the capillaries open up as a wide network of tubes, so the resistance is relatively low. Now, what governs the resistance? And again, we have resistances here and here and here and here, and it is by playing, we'll see that in the next lecture, by playing and by modulating this resistance that we will adjust the blood flow. Again, the basic rule being the heart pumps blood, keeps the pressure going, and in function of the resistance of the degree of opening, more or less blood will go. If I'm resting, not much goes. Do I have limbs here? You know, to my muscle, like right now, not much blood goes to your leg. If you start running, then suddenly more blood needs to go. We open the faucet. We reduce the resistance, and the heart has to follow and pump blood. Okay? So very simple. Always think of my water tower and my faucet. That's all you need to know to understand that. here we go again. Degree of opening in the individual tissues, if the pressure remains the same, flow will continuously be adjusted to the need of the tissues. And resistance is governed not only in hemodynamics, but this is hydrodynamics, by Poisson's law. If you have had courses in physics, you've heard about that. And that says, you know, basically it says that the resistance offered by a tube is function of the length of the tube. If you have a given pressure here and a very long tube, at the end the pressure would be very small. It is also a function of the viscosity of the fluid. If you have a syringe and you want to push fluid with water, it's very easy. With oil, you have to squeeze a lot more. And then the other determinant of resistance is the diameter of the tube. Again, if you want to push fluid through a syringe with a needle, the thinner, the smaller the needle, the more you have to push. Okay? We all understand. It's very simple. But the key, of course, is that the resistance is affected by the length and the viscosity, but is inversely related to the radius, but not in a simple way, to the fourth power, which means that small changes in diameter will have a very important impact on resistance. So to increase resistance very much, you don't have to necessarily close the tube totally down. The moment you start reducing the diameter, your resistance will start to go. So remember this. This is a very important equation in physiology. And again, the changes in diameter are caused in all arteries and veins, but particularly in resistance vessels, because they contain those muscle cells. Muscle cells that are contractile cells. They're not as well organized as skeletal muscle or as cardiac muscle. They're individual cells, but they contain contractile proteins, they contain mitochondria, they're a contractile machinery. As I say, they're arranged circularly around the lumen, and when they contract, they will reduce the diameter and thus increase resistance. When they relax, they will increase the diameter and thus reduce resistance. And as a consequence, if blood pressure remains the same, if they contract, flow will go down. If they relax, flow will go up. Okay? We understand that? No questions? Good. So you all understand it very well. I'm very pleased to hear that. I must have done a good job. Yeah? And thus, those blood vessels contain those contractile, the smooth muscle contain the contractile proteins that will interact like in other skeletal muscle. I don't go into details today on that. And when energy is generated, when the calcium in the cell augments, those contractile proteins will interact and the smooth muscle will shorten. Okay? Good. And what can cause contractions or relaxation? We're back to the first lecture. All the signals that can get on those smooth muscle cells from hormones, from all kinds of things that can hit the smooth muscle cell, and eventually, mainly receptors and ion channels, receptors that are activated by agonists, ion channels that are open, and eventually this will lead to changes in calcium concentration in the cell. If the calcium goes up, the cell contracts, the cytosolic calcium, the cell contracts. If the calcium goes down, the cell dilates, relaxes, and the blood vessel dilates. Okay? Again, we may come back to that later on if we have more time. So what do you have to remember? Peripheral resistance is determined mainly at the level of the precapillary arterioles, the resistance vessels. The individual resistance are determined by the needs of the tissue cells. That's the basic equation. And by maintaining the arterial blood pressure constant, adequate perfusion in function of the individual needs is ensured. Remember that individual resistance is related to the force power of the radius, inversely related to the force power of the radius. Okay, then we move on to the exchange vessels. And that's where the capillaries. And here we start off by telling you something that we haven't talked about yet, the velocity of the blood, which is the lowest. What is velocity? Well, velocity is the speed. A car flies by at a certain speed, 60 kilometers per hour. That's velocity. Now, if you look at the heart, it pumps blood. It pumps blood at, let's say, 5 liters per minute. This gives a very high velocity in the aorta. Okay? Now, as we go down, the aorta branches, and that branch branches, and that branch branches, so that the diameter, the total area, cross area, covered, goes from the aorta where it is very small, it becomes bigger and bigger to become area here. That's the one I want. It's very small here. It becomes bigger and bigger when it reaches the capillaries, and then they're rebundled and they become the large veins. And there it's the diameter, the cross-sectional area is about the same as the aorta. Now this is a closed system. So in each one of those sections, global for the body, 5 liters per minute have to go through. Unavoidably, that means that here it will be very fast, but then as we go, branch, it will slow down, slow down, slow down, slow down, and then pick up again. And when we go back to the veins, it is as fast almost as in the aorta. Do you understand that? So, velocity is the smallest at the capillaries. And this is very healthy because that's where the exchanges occur. Imagine that you're in an airport and you go to pick up your bag. The carousel is turning. It's turning very slowly so that you can pick up your bag. If the carousels were turning very fast, you could not pick up your bag. Velocity versus exchange. You understand? So it's crucial that the circulation slows down and then picks up again. Isn't that a beautiful system? It's incredible, isn't it? Yeah. Okay, so that's where the exchanges occur here in the capillaries. So, the slower velocity in the smaller blood vessels provides optimal time for exchanges for gases, nutrients, waste products at the level of the tissues. And what are the cells that are involved here? The endothelial cells. The capillaries characteristically have only one cell layer. The only thing they have is the tapestry. A monolayer of cells that separates the blood from the tissue. Now those cells, in the rule, endothelial cells always touch each other. But there can be passages between the cells. And depending on the tissues, the passages are average, very large, or extremely small. In the brain, they're very close tight. the blood-brain barrier. Very good. In the liver, we have what we call fenestrate windows, because the blood from the gut loaded up in the gut, we pick up all the foodstuffs, lipids, glucose, everything. That goes to the liver, and there we have to store it, metabolize it, change it to our own proteins and our own material. There we need to take up a lot. So there the holes are big. In glands where we, exocrine glands, where we want to release fluid in the outside world, the gaps are bigger too, or can become bigger, we will see that. Okay? So one monolayer of cells that separates the blood, and in the capillaries the blood cells can, have to almost force their way through it. Now, the exchanges are complex. They can go purely through physical laws. We'll come to that in a minute. But there also are systems in the endothelial cells that can actively pick up. I think we've mentioned that last time. Let me go back a few slides. Remember? Transporters. I talked about that. A system that at the cell membrane can recognize a molecule, pick it up, turn around, and put it inside the cell. Well, in the endothelial cells, we have systems like that will pick up substances, transport it through the endothelial cell, and dump it in the tissue. So the active transport is possible. But the main exchanges still are through physicochemical forces. And those are governed by, those exchanges are governed by two forces: the hydrostatic pressure and the colloid osmotic pressure. The hydrostatic pressure is simply the actual physical pressure that the blood has at that time. Now, if you remember, blood pressure was 120 leaving the heart and was going down to reach about 30 millimeters of mercury by the time the blood presents itself at the entry of the capillary. Now, that is a force that pushes on the blood. Now, imagine a tube with holes in the side. You put pressure, what will happen? That force will push fluid towards the tissue. The hydrostatic pressure drives blood, fluid from blood, water and electrolytes and solutes, glucose for example, drives that toward the tissue. But the blood is a complex mixture. It is a solution of proteins and sugars with a suspension of cells. But let's talk only about the solution. And that solution, because of the amount of protein and sugars, etc., and ions, has an osmotic or even a colloid osmotic pressure. Do you know what a colloid osmotic pressure is? That's a pressure, the attraction to fluid exerted by a suspension of protein. If you do, have you ever taken gelatin and put it into water? Then it will dissolve and swell. It's the same thing. If you take a piece of sugar and you put it into water, it will suck up the water or the coffee. That's what we talk about. In that tube that has holes, there is a solution of proteins, sugars, etc. And that tries to attract fluid from the tissue. And now the best one wins. If hydrostatic pressure is bigger, goes to the tissue. If colloid osmotic pressure is bigger, goes back into the blood. And the trick now to understand how it works is that as blood comes here happily at 32 millimeters of mercury, it flows through this relatively small tube. that offers resistance. So the pressure, the hydrostatic pressure, will drop. At the end of the capillaries, it's only 15 average millimeters of mercury. But at the beginning, this pushes fluid into the tissues. And that concentrates this suspension of colloids, etc. So as more fluid goes to the tissue because of hydrostatic pressure, the colloid osmotic pressure of the blood becomes bigger and it starts to attract. So we go from a point where fluid goes into the tissue to nothing, and then at the venous side of the capillaries, we start to suck up fluid again from the tissue. What are we doing? We are washing the tissue cells. Think of my little beast in the water. That's what we do here. We continuously refresh the milieu around the cell. And that works day in, day out for all tissues of your body. It's quite an amazing system. And most everything goes back into the blood. There is a little loss of fluid. You know, colloid osmotic pressure never totally makes up for hydrostatic pressure, so there is a little bit of fluid. But that is drained then by another system that we call the lymphatic system. And I will not talk a lot about that today. But the lymphatic system is important because it kind of drains the tissue. So if there are pieces and bits of cells here, if there are microbes here, they will end up in the lymph system. And down the stream here we have the lymph nodes that are a barrier against infection, etc. And that will eat up everything that shouldn't be there. But that's a different story. The lymph system, we usually don't cover that so much in the circulation because it's very little fluid, but very little, but if it's a long period of time, you know, if lymph flow is occluded, and theoretically this can happen by tumors or by certain parasites, then the tissues will progressively swell. You certainly have seen elephant legs in people. You know, this is because the lymphatic system, you know, is not draining properly. Progressively, the limbs will swell. But that's another story, not for today. So here we go. This what you have to remember is this unique equilibrium between those two forces: hydrostatic pressure pushing in, colloid osmotic pressure sucking up. And at the end, we wash the cells of our body. Okay. Now, let's try to imagine a tissue that is active. That needs, if it is active, what does it do? It needs more oxygen. Oh, I didn't say it, but the exchanges, the gas exchanges, are purely physical. Following the gas laws, you know. That's depending. More oxygen at the beginning goes to the tissue, low oxygen, more CO2. At the end goes back in the blood. Okay, now we have this tissue and it becomes active. So if it needs more oxygen, more foodstuffs, because it is active, it will generate more metabolites, has to be washed away better. Okay? Very simple proposition. How can we achieve that? But we achieve that by local vasodilatation. What does local vasodilatation cause? Well, it will cause its opening of the arterioles. That means the diameter gets larger. That means the resistance of this circuit, part of the circuit, gets less. That means that the hydrostatic pressure here gets bigger. So the capillary pressure gets bigger, and we force the system towards pushing fluid with foodstuffs, oxygen, etc., towards the working tissue. Do you understand that? And then, you know, the danger of that is that there is more blood here, but we'll come back to that later on. So if we want more foodstuffs, all we need to do is open the faucets. And as a consequence, we will have more washing of the tissue, more bringing new oxygen, new food source. This is in pathological situations. But this can be, we'll see that later, this can be governed by the needs of the tissue, but such exchanges can also be caused by a number of molecules that we may discuss next time, the aldehydes, and histamine is a good example of that. You know what histamine is? That is the substance that is being released, from those cells, these histamine-containing cells, mast cells, etc., that will be activated during allergic reactions, etc. But not only during allergic reactions, every time you scratch yourself. Now, if you scratch yourself, what will happen? If you scratch long enough?
Reddish.
Reddish and it will swell. Why? Well, histamine is released, and it will, this would be the starting situation before you scratch. No histamine, arterioles in your skin quiescent, little blood just to keep the skin alive, little exchanges, the veins are just pumping things away, no problem. Now we scratch, or we have an allergic reaction or whatever, or during inflammation, we suddenly release histamine. And histamine is a wonderful molecule because it really works on the three components. It will open up the arteriole, increasing hydrostatic pressure. It will increase the number of openings. Those openings between endothelial cells can become bigger. If the endothelial cells shrink, the openings between the endothelial cells become bigger. So less resistance for the flow. And at the same time, histamine will shut down the veins so that the pressure remains higher in the capillary. And this altogether causes the increase in fluid towards the tissue. The redness comes from this. More oxygenated blood, it becomes red. The swelling comes from this. So histamine is a prototype of the molecule acting at the microcirculatory level, but the same is true for bradykinin or for serotonin, I don't think. And I said a few words about lymphatic drainage. So what do we have to remember about the exchanges? Well, the permeability per capillary varies depending on the tissue. Blood-brain barrier, very tight, liver, quite open. It's the balance between the hydrostatic and osmotic pressure, and I didn't insist on that, but of course the forces to push in the tissue are in equilibrium with the resistance of the tissue to accept fluid. So it's an equilibrium between osmotic pressure in the tissue and the blood, and the hydrostatic pressure in the blood and in the tissue. I should have said that. And that governs the movements of water solutes. The exchanges, the balance changes with variation in diameter of precapillary vessels. The little excess fluid transiting from the blood to the tissues is drained by the lymphatics. Active mechanism transporters, I've mentioned that, contribute for specific molecules. And the gas valves, you've seen somewhere else. That really is simply a matter of physical diffusion. So, a crucial aspect, and don't forget, this is the ultimate goal of the circulation. This is the ultimate goal of homeostasis, to make sure that at that level things are possible. Okay. Now, we have done all of those wonderful things. Now the blood goes back into the veins. What is the function of the veins? Well, the function of the veins, obviously, is to return the blood to the heart. Now you have to realize that the heart, the right heart, and over the lungs on the left heart, that the heart will pump. But it can only pump what it gets. If you have a pump to water, and you want to pump, but once there is no more water in your well, you cannot pump anymore. Very simple, the same in our body. So I always say, because I'm a blood vessel man, to people like Professor Peter Kang, who is a heart man, I say the heart is very stupid. It can only pump what it gets from the veins. But this is true. So this implies that if we want this to accelerate, we have to make sure that there is more blood that comes back to the heart. And this is achieved by the venous system. The venous system, if we calculate that on the average we have 5 liters of blood, but 70% of that blood is in the veins. And the venous system is an active reservoir that can, when needed, adjust the filling of the heart. Okay? Good. How does it do that? Well, it does so in different ways. When I say the veins, what is the next one? When I say the veins, this is a big term, but basically you have to dissociate between parts of the venous system. And each part, again, plays a specific role. Some of the veins are actually very passive. Those are the veins in the skeletal muscle. Those are the vena cavae. Those are basically big tubes that return blood to the heart. The skin veins are very active, but their main concern is not the filling pressure of the heart. Their main concern is they are the radiators of our skin. If you look at my veins, it's cold in this room. My veins are shut. If it were warm, my veins would be open. Why is that? Well, because the veins are the heat exchanger. Our cutaneous veins are the major heat exchanger in our body. And that dominates the function of the cutaneous vein, excuse me. Although there are other, I think we'll see that not next time, but the time after that. So there are other aspects. The main regulation of filling pressure is in the splanchnic veins, the veins in our belly. And to understand that, I will have to already say something that I wanted to say later on. You will, if you think about hydrostatic pressure, let me see whether I can have it. Yeah. When you think of our species, what is unique to mankind is that we can stand up. Almost unique. Some apes do it too. And the advantage of standing up, of course, is that you can see very well. And although we are a weak species, the fact that we can see well and can react and are intelligent makes us able to survive. But standing up from the hydrodynamic point of view costs. In the sense that your heart will generate pressure, but on top of that, you have the hydrostatic forces. If I stand up, and let's assume that I put the level of pressure that comes out of my heart, and that I put, okay, this is the 0 point, everything above the heart would be negative, everything Through gravity. And actually, if you measure, if you look at the arterial pressure, let's say the mean arterial pressure would be about 95 milliliters of mercury here. If we raise my hand, here in my hand it will only be 35, because we have to subtract this hydrostatic column. While here it will be 185, because we have to add this hydrostatic. You understand? So that's the price that we pay for standing up. And we'll see that later, for the circulation, standing up in the morning is a very dangerous moment. Because you suddenly bring in this. As we lay down, everything is the same. As we stand up, we are in trouble. Well, the splanchnic area is here. This is the zone in our body that is the least subjected to changes in gravity. And this is, oh, let's go back to my slide. This is where we can adjust at low energy cost. We can pick up blood or release it to meet the demands of the filling pressure. So the splanchnic veins are the key dynamic part of the venous system in terms of vascular control, in terms of the control of the circulation. So, the veins constitute, we call that capacitance, this volume, capacitance reservoir of the circulation responsible for the moment-to-moment adjustment of the return of blood to the heart so that the heart can continue to pump what it needs to do. Remember, the heart is stupid. It can only pump what it gets, and it gets it from the veins. Okay? Good. Now, what determines the content in a vein, of course, is the dimension. And that is governed by another basic physical law, Laplace's law, that says that wall tension is function of the pressure and the diameter. So the bigger the pressure, that's an easy one to understand. So the degree of opening of an elastic tube is determined by the distending pressure, that would be the local arterial, or in our case venous pressure, and the wall tension, the elastic behavior, the muscle tone. So if a wall is very rigid, like in the large arteries, it will distend, but not very much, and have great energy and give energy back. If the wall is very elastic, it's the Laplace's law is the balloon law. At the beginning it's very rigid, you have to push very hard, and then it becomes very good. And characteristic of of most veins is that they are very distensible. Now this is a jugular vein, big vein in the neck of an animal, but it's the same in humans. And what the investigator here did a long time ago, what the investigator did, I was already doing science at that time. He took such a